Welcome to Calculus. We conquer our fears and flex in the face of adversity. On this episode, Stevenson will demonstrate
Here's another example of how we would find numerical implicit derivatives. So the question says, find the tangent and normal to the ellipse, and they give us the equation of the ellipse at a given point. Now, they also give us a nice picture. Oh, it's so pretty. Now, an ellipse is basically your mathematical term for what you might think of as of an oval, okay? When they say tangent, though, that means they're asking for the equation of the tangent line. Well, we know that's a point and a slope, and the slope is the derivative at whatever value we're looking at, right? Well, the normal is just the line perpendicular to the tangent. So the beauty of this is that all we need to do is figure out the equation of the tangent line, because the normal is going to go through the same exact point, but the only difference is that the slopes between the normal and the tangent are perpendicular. So that means they are opposite reciprocals. So they're opposite in sign and they're reciprocals of each other. So all my work is basically going to be spent finding the equation of the tangent line, and then all I have to do is modify that to then get the equation of the normal. So this is a problem out of your book. It's on page 171. So the first thing I need to do is find the derivative. Well, this is an implicit function, and you can tell because look at how it's structured. X and Y are on the same side, and algebraically there isn't really a way to separate them. So we're going to use implicit differentiation. So the first step, don't panic, I know you're panicking right now. The first step is to find the derivative. Well, in order to do that, first we break it down. We're going to do the derivative on both sides. So if you see in the book, they break it down by showing you're going to do the derivative individually of each part. Now, why do we do that? Because of the sum and difference rule of derivatives. Remember that? Now we look at the derivative individually. The derivative of x squared is just 2x. That's just power rule. Now it's minus. Be very careful with those negatives. Time and time again, people jack these up. The negative, okay? Put it in front, think of that as your constant multiple. And then parentheses, do you see we have product rule? So this is the first, which is x, times the derivative of the second, which is y, which is 1 dy dx, plus the second, which is y, times the derivative of the first, which is dx dx, that's just 1. And then close your parentheses. So this is product rule. Plus, now it's the derivative of y squared. So it's 2y, because do regular power rule, and then times by a dy dx. Remember, every y term will generate its own dy dx term because it represents a hidden or implicit function. We don't know what it is, and the beauty is we don't need to. So, and lastly, the derivative of 7 is 0. Can't forget my constants. So when you look at this problem, do you see how there's two y's? That means I should have two dy dx terms, and I do. One inside the parentheses and one without. So that's the first step. The first step is just go through and take the derivative across the whole thing. The second step now, kind of in this case, blends with the second and third step of that flow map, which basically means start to regroup things. So what I'm going to notice is my 2x can be subtracted to the right, so there it is. I also notice inside my parentheses here, this is just 1y because dx dx is 1, but it's going to be negative because of distributive property. So this is really a negative y, so I'm going to add it to the other side. So that's where the y minus 2x comes from. Well, what does that leave? It leaves a 2y dy dx, and it leaves an x dy dx, actually a negative x dy dx. So those two are left on the same side. That would be step 2. Step 3 means you can actually factor out the dy dx's, so it would look like this. So remember, textbooks like to skip a couple steps at a time. So it's super important to slow yourself down and try to read step to step and see where the process is going. Now the last step, which is step 4, this quantity I would divide to the other side to the right, and you end up with what you see before you. Now remember, let's not lose sight of why we're doing all this. We're doing this because we want the tangent. So we essentially want the equation of a line. So that's dy dx. So that will give us the slope at any point we want on our ellipse. Well, what's the point we're looking at? -1, +2. So the next logical step would be step 5. Remember, I told you that's an optional step, right? We don't always have to do it. In this case, we do need to do it. So we're going to take our derivative, which was right here, and we're going to evaluate it at that ordered pair. Be very careful. The -1 will go wherever you see x. The +2 will go wherever you see y. Order of operations tell us the slope is 4/5. So we have everything we need. We have our slope, which is 4/5, and remember, we have the point. It was given to us in the beginning of the problem. Remember, that has to be given to us in order to find the derivative, because it's an implicit function. So the equation of the tangent is just y minus 2 equals 4/5 times x plus 1. So this is point slope form. And now the normal is super easy. Just take the slope from the tangent and do the opposite reciprocal. So since the tangent's slope was positive, the normal becomes negative. And if the tangent slope is 4/5, then the normal is 5/4. And there you have it.